Jaewon tell us about lagrangians for non-lagrangian theory.
Thank you very much. It's a great pleasure to be here, and I'd like to thank the organizers for organizing this wonderful workshop at a very wonderful venue. I don't think I've ever been in such a wonderful place for a physics conference. So today I'm planning to present some series of my work, mainly in collaboration with Kazunoko Maruyoshi, and also with Perry Agarwal and Anthony Maroni. The outline is as follows. I'd like to first briefly explain, to remind you what this Archer-Stavros theory is. And this is probably one of the most well-known is non-lagrangian superconformal field theory. And the main part of my talk will be about describing some n=1 gauge theory that gives you some kind of high energy description of the n=2 Archer-Stavros superconformal field theory through RGO. And hopefully, if things go as I plan, in the second part of my talk, I'm going to talk about more like slightly general context. And historically, like our discovery was not this was discovered in '95. But like we originally thought of doing this kind of study, and we somehow got this AD theory by chance. So I hope to say some more open questions and problems in part 2. Okay. So let me give you a brief introduction to the AD theory. As you all know very well, uniform n=2 gauge theory has a Coulomb range. Which is parameterized by some gauge and operators such as like trace square and so on. These operators parameterize the Coulomb range, and in the generic point of the Coulomb range, say if I give a expectation value to the scalar field as a scalar vector multiplier, then generically you break gauge symmetry down to U1 to the power. And at this Coulomb range, you generically have some electrically or magnetically charged particles. Because particles charged on the wheel. And the beautiful thing about cyber-Newton theory is that you can determine this mass of weak-phase particles and also the effective pre-potential at any point in the Coulomb range by using this cyber-Newton geometry. And so in this Coulomb range, so as you move in the Coulomb range, you can change. You'll be changing the mass of particles. So sometimes it's possible to tune your find some logos where some weak-phase particle becomes massless. And there might be another logos where different particles become massless. And when they are electronically non-local, visually non-local, which means that their carrying of the charge is non-zero, then at this point, you effectively have some QED-like system with electrically and magnetically charged particles at the same time. And this is described by superconformal theory. And that's this point is described by what's called Archer-Stavros theory. So I'm not so good at history, but like I looked into some older literatures where like older people, like back in the 40s or 50s, people were trying to write down some lagrangian for electrically charged particle and magnetically charged particle at the same time, and it had lots of issues apparently. So also it wasn't really clear whether such a kind of system even exists as a quantum field theory. And our just actually show that such a system indeed exists as a nice quantum field theory. So that's a bit of history. And since we are not breaking any amount of supersymmetry, this is still described by n equals 2. And this is still just another superconformal field theory that has n equals 2 system. So the first example of our Aristotelic theory was constructed by using SU3 pure field. Or there's the equivalent description that can be obtained from SU2 with one flavor. By tuning your mass parameters and the flow bridge parameter at the same time, you can land on one like this. And at that point, if you zoom in your cybervision geometry like this, it's unfolding. And cybervision 1. Actually, this is probably not the original way of writing down the curve. It is present, but if you see this, if you turn off U1 and U2, then this really describes A2 singularity. And that has something to do with this SU3. And in modern times, for the past 10 years or so, there has been many interesting discoveries, like gives you large landscape of Marcus Douglas-like superconformal field. And the unfortunate thing is that the nomenclatures are very inhomogeneous. There are just so many different names of the same theory. So this theory, this Archer-Douglas theory, sometimes called A2 theory, or sometimes called A1, A1, 2, or H0, or I2,3 theory. There might be more.
Yeah, Roman numeral 2 theory. Roman numeral 2.
Oh, 2. Okay. So there seems to be no universal one, or there's nothing really dominant. But A2 theory for sure is because cybervector geometry is A2 singularity, and this double D label notation comes from the shape of the BTS quiver. And this H naught or I2,3 stems from, or a way of understanding this is that H0 describes singularity profile in F theory, where if you probe 3 plane, if you put probe 3 plane probing that F theory geometry, and that on the wall volume theory of D3 plane, you get this thing. And this is due to the class S description. And so the class S, so you compactify 62 theory on a Riemann sphere in this case, with some singularity there. And this I2,3 really labels the type of singularity around this point. And actually that singularity is indeed described in this way. If this is x equals infinity. And so this 2, 3 is 2, 3 of a squared and c cubed. So there are a few things that you can learn from that type of curve.
Maybe you could also call it the Death Star theory.
Oh. Nice addition. Yeah, but but there's that star 1 and 2, but probably no Death Star 3, 4, 5, 6.
Sometimes we play with the DVD because of the sequels.
So, anyway. Yeah, so from that curve, I can get some simple thing. So from the dimensional analysis, you know that this the mass is given by the absolute value center charge, which is given by integral over this higher differential. So that says the dimension of this guy is 1, the mass dimension. So that gives this relation. The dimension of x plus dimension of z has to add up to 1. And from the side of the curve, we find that twice of x is 3 times z. So we can easily solve this. So that's the dimension for x and z. And from here, you can use the dimension of the parameters u1 and u2. And u1 will have dimension 4/5, and u2 will have dimension 6/5. And these things pair up in n equals 2 supersymmetric theories that in the n equals 2 superspace measures that your interaction can be written this way with the scaling dimension being equal to 2. So the interpretation is that this is a Jaewon operator and this is a parameter associated to that. So this suggests that there is an operator of dimension 6/5 in this theory. And as you see, that deforms this hybrid in geometry. So it is indeed the parameter of the Coulomb range. So Coulomb range is kind of generated by U2. And that has dimension 6/5. So you cannot hope to get dimension 6/5 from n equals 2 gauge theory, right? Because in n equals 2 gauge theory, the scalar vector multiplier has dimension 1. So typically, you form the gauge unit operators in this way. So integer dimensions are natural. But fractional dimensions are not that easy to get if you want to write down lagrangian that preserve n equals 2 system. There are a few other things that people have computed for this theory. This H0. So we know the center charge. Inter charges of this theory. This guy. And so these numbers are the smallest A and C among the n equals 2 superconducting field theories. And especially for this guy, it was shown by Pedro and friends, Leandro, Ramirez, and Saul, that for any interacting n equals 2 CFT, you should satisfy this relation. So the central charge C has to be greater than or equal to 11 over 30, and that is saturated by this Archer's numbers theory, H number. So in some precise sense, Archer's numbers theory is the minimal theory, minimal n equals 2 CFT. Another clue is that the chiral algebra corresponding to this guy, the right H0, is given by the simplest non-unitary binary model. C plus minus 2 that's the lagrangian. So this is the simplest reversal non-unitary binary model.
What makes it the simplest? I mean, is it just that it has
It has the smallest number of primers.
parameters?
Yeah, it has only 2 of dimension 0 and minus 1/5. So Ising model has 30, but this has 2. So it's simpler. found that for A2 and 3, the chiral algebra is given by the Virasoro minimum model. This where you know this central charge is given by this. These are P and Q. And they're all negative for these ones.
So just when you say it's given by, you mean is conjecture to be, or is there's good evidence, or is proven? When you say the chiral
Okay, I cannot say it's proven, but it's very likely this is the case.
Because what is the evidence? What is the evidence that that's the case?
Well, first of all, you can directly get the central charge. That's the first piece of evidence. You know, let me remind you that the central charge of chiral algebra is given by -12, C40. And C40 has been completed for this guy. Say, if you put 11 over 30, then you get -20 over 5. And also, this theory does not have any global symmetry beside R symmetries. So the minimum thing that you can hope to get is Virasoro for this theory. And luckily we have this special value like -22 over 5, where at which like there's a null state at level 4, and that can be actually translated into well, at least it's consistent with C equals 11 over 30, because as C equals 11 over 30, you actually expect to see that null state.
So what is the disconnection between unitary and non-unitary between 2D and 4D?
What do you mean?
The negative sign. Is there any understanding?
As far as I know, it's a result of computation. And they all has that.
Yeah, let's leave it at that. Just, I mean, you could basically some correlation function that satisfies unitarity, at the base of the constraint of unitarity, and you end up with something that's completely neuromorphic. In the process of doing this twist, you have to introduce some signs. So a two-comma function that has plus reflection positive in 4 dimensions, it becomes these two negative norms in the chiral algebra. And then certainly, for example, this -12 is just universal. You can say the two-point function in 4 dimensions twisted to the two-point function. There's some subtleties of normalization that I'm skimming over here. You get the negative -12.
There's some understanding. So, given that the two-dimensional theory is non-unitary, is there some understanding why one might pick out a minimal model on all possible non-unitary CFTs with that simple charge?
That's an interesting question, because as far as I know, I don't know how to get the other other PQ. So you get 2,20 plus 3 from A2 and theory,
Right.
but this is even. For odd, you don't get Virasoro minimum model, you get something else.
Well, let me sharpen that question. So the thing that distinguishes these guys is indeed, you know, that there are null vectors at certain levels in seconds, right? And what does that translate into something in the 4D theory?
Yes.
Presumably it does.
Yes.
Yeah, it translates into null states in
In the 4D,
the absence of certain
Right.
we use it in 4 dimensions.
Right.
Why that has to be the case, I'm not entirely sure. But there's also the statement that the associated variety, right, we should be able to, now we have some new insights. Mostly, like Chris and Leonardo have some new insights that you should be able to find the Higgs branch from the chiral algebra as something that's called a variety, associated variety. But in order to associate it from this variety to the chiral algebra, you need to have some kind of, well, I'm not sure I want to call it null set, but some kind of relation in the chiral algebra. So
Yeah, I mean, essentially.
if you say let the central charge, let's suppose the chiral algebra is just pure 0,
Right.
then I think you need to have need to be at the very least in one of the minimum model cases to have a null state in pure 0.
That is what the Katz formula tells you. Those are
there's this map of between 40 n equals to CFTs and chiral algebras. But this map is not like one-to-one. Like you have, there are some chiral algebras that has no 40 origin, or vice versa. Well, if you're just given 40 n equals to CFT, then you can always come up with some associated chiral algebra. But the other way is not always. It's not always realized. But actually about this minimal model or some kind of weak notional rationality should play a role here, because this is slightly out of copy of my talk, but nevertheless I have to mention. That is, the partition function of the chiral algebra computes the limit of superconformal index. So if there's no null state, then the superconformal index might look very trivial. Right? It should be something like 1 over eta to some power, and that's not the case. So presumably there is some notion of rationality for the chiral algebras up here from the Fourier equals to CFT. I don't know how to make this notion precise. Mathematicians have some thing to say that I don't. Okay, so let me. I want to give you one more example, H1. By the way, there's this series, H0, H1, H2, E4, E6, E7, which can be all realized from F3 by three-grade probe. And this is called Daily exceptional series. If you add G2 here and F4 here. So it has been an open question whether it's possible to realize this G2 F4 theory as a rank 1 n equals to CFT. But anyway, so I just told you about this, and let me give you a similar explanation for H1. So H1 theory, the high-derivative geometry is simple. It's squared over like c to the 4th. So that this guy is called I2 4. This is a Destler 2. Higher similarity. So and I can add a deformation. I add deformations to it. So, and it's very easy to compute the dimension of x and z. Dimension of x would be 3/3. Yes. So that gives me dimension of 1 to be 2/3, and 2 to be 1, and 3 to be 3. And this has dimension 1, and this is actually an S-prime.
What sets the overall scale?
The
Sure.
cyber
That's
set
like
one for.
Cyber with differential.
Yes. And here, this is Coulomb parameter. So it turns out this theory has SU2 global symmetry. And the conjecture is that the associated chiral algebra for this guy is given by this very simple SU2 affine Casimir algebra with level being -4. And actually, this level comes from the 40 flavor anomaly. For this theory, it's given by a third. It turns out this is also the bound for the SU2 n equals 2 CFT with SU2 global symmetry. This is studied by Manuela and Pedro.
Regarding your comment, what do you do with 3.7.5?
Which half?
There's it's not the whole list. The list you get is not the whole list. In the list of Chivitan.
What?
In 7 and 8, there is 7.5.
Yeah. I recently read about it.
You know what? So,
It's an interesting question. I don't know. But yeah, of course, you can try something very simple sometimes. Assume that there's, yeah, I cannot say anything because I don't know of concrete 40 theory that realize this goes.
Well, what? I'm sorry, but what is E7.5 as a symmetry group?
has a joint representation of 56 plus
So it has, so
190.
this guy has 56 and this guy has 56 plus 1.
There's additional 1. So it has dimension 190. So if you
So if I wanted to talk, say, describe it in terms of a Lie algebra of a,
no, this is only representation theoretic. You place the dimension formulas of representations using the parameter, and they are all parameterized by integer numbers. And if you pick the right integer number, you get all of these dimensions. They fit nicely. And,
so isn't there a Coleman-Mandela theorem which tells us it has to be a Lie algebra?
Numerology.
you're talking to the sources.
I mean, one way for me to motivate this E7 path is from numerology. That is, if you look at this dimension of the full range operator, that goes like 6 fifths, 4 thirds, 3 halves, 2, 3, 4, 6. So what's happening to this file?
And this is the same line of reasoning that we use in these papers.
But if we're talking about field theories, there's a Coleman-Mandela theorem which says that the global symmetry groups are going to be compact Lie groups, where the symmetry algebras will be the Lie algebras, compact Lie groups. Anyway.
And you have an existence of a lagrangian.
That doesn't require a Lagrangian.
It's just 7 is a algebra. It's a semi-direct product of E7 with a 57-dimensional representation plus maybe A1. So it's a algebra.
No, but I'm not about like
And it's
compact.
but it's not, yes, it doesn't produce it.
Yeah.
So maybe there's a non-unitary.
Right.
Good point.
So it's going to unitary.
Well, I mean, by that argument, since C2, C3, C4, and C6 are crystallographic, Z5 should be 2, even though that doesn't work.
Well, one of the challenges for you is to construct 40n equals to CFT where chiral algebra is given by Ising model, for example. Can it be done, or can you disprove such a possibility? I don't know. I mean, tantalizingly, if you just use the C2D and C40 formula, that has minus 1/24, right? And that is like the negative of the chiral, is that right? Something like that. There's something tantalizing about it.
If I understand correctly, Leonardo observed such a symmetry in his studies. Leonardo, I think he's seen this E7 one way or another. I don't know the details. He was reported.
I think for now we should have faith in Coleman and do that.
All right, so let me move on. There are a couple more data that people have discovered about H0 and H1 theory, that is, you can compute Shor index, either by using this chiral algebra, or there's also connection to this this is according to the correspondence Ellie talked the other day, that there's a relation between T and a superconducting index of So we can use this relation and try to find a index formula for these guys, these kind of fields. And turns out we can do it for certain cases. This has been studied by Buikan and Shinaka and also by myself. So that produces some result which is consistent with the chiral algebra. So I would say that's under the hint that the chiral algebra described by minimum model would make sense. But I think that it would be desirable to have like a direct construction or maybe more rigorous proof why the chiral algebra or Archer-Stowers theory is indeed given by this minimum model. So far it's a guess and check.
For chiral algebras, we have a lot of guesses. We have very, very little
Yes.
solid proofs.
That's true.
Chiral algebra to any for any n equals 3 to 4 dimensions is given by whatever we project it to.
That's true.
How do you prove it? Is there any idea of how you actually prove it?
I don't really know.
So
There. I mean, in the class as story, for example, so, or more generally, you gauge. If you do gauging, right, you're thrown into some VRC problem, so that's a prototypical thing of something that you can try to prove mathematically. So we know chiral algebra free theory, so you can build your chiral algebra from free theories.
Right, for free theories it's rigorous.
Let's start from that. That's something you know. Maybe you want to make the extra assumption that you know how to close a function, which is not pre-conjecture to the quantum critical circle of reduction. And then if you're a mathematician, you can try to unclose the function, open it up. And so now you have some functions and operations that you can do on basic building block chiral algebras, which should allow you to prove that what the chiral algebra is more complicated.
Okay, now let me move on to the next step. So I'd like to give you a n equals 1 gauge theory that describes this H0 and H1 Archer-Stowers theory. And so here's a matter content. And the gauge group is given by C2. By the way, this is all n equals 1. N equals 1 chiral. Adjoint and 2 doublets and 1 singlet. And the interaction is given by this potential. And I'm suppressing all the indices here. So if you see this, you might think that this is this this has 2 high dimensions, so you might want to just throw away. But it turns out this is one of the so-called dangerously irrelevant operators. So it started life as irrelevant operator, but as you go along the algebra, it ends up being relevant at some point. So because it gets large anomalous dimension. So this is a theory that I propose that describes this H0 theory. So this is the flow of H0 theory. Up to some sort of theta. So if you look at the gauge theory, it turns out this theory has 2 U1 global symmetry, that's which is anomaly free. U1, so one of them should be R symmetry. And there's some global symmetry. But here, the superpotential and the anomaly free constraint is not going to fix the R charges for these fields. So, but there's a way to fix that R charge, thanks to Ken introduced it right away. It's called Davis notation. So the way to fix the R charge is to minimize the A function. And for n equals 1 supersymmetric theory, the conformal anomaly A can be written in terms of two anomalies of the R symmetry. This way. You can also do the same thing for C. The procedure is that you plug in some trial R charge and compute the trial A function. Say that the superconformal R symmetry should be given by some linear combination of all the ones that we have. And this R, this epsilon is fixed by minimizing this A function with respect to epsilon. And this will pick the correct epsilon for you. And this is very straightforward and easy. So let me do it. So here, from the superpotential, from the first term, from the first term of superpotential, I have this relation, R chart of 5 plus 2 times R chart of 2 should add up to 2. And from the second term, I have R of 5 plus R of 2. In deduction to this R symmetry has to be anomaly free. So this thing should be 0. And that will, so if I compute this, I get first C, so that coming from, this is coming from a genome of the CG group. And there's also another one coming from 5, which is that one. And plus CG fundamental for Q, and also Q prime. And that has to be 0. And this is 2. And this is half for NC2. And you can immediately see that there are like 4 unknowns with 3 relations, so it's not going to fix all the R's. And the R is fixed by maximizing this trial A function. Let me keep this. So if you work that out, you can plug it into Mathematica, and it turns out that I get a real value. R chart of 5 is something like this. And you see that this is below the unitary bound, which is 2/3. So there's, okay, well, this is not that. Phi itself is not a gauge invariant operator. But if you compute R to the base phi squared, this is like 0.31. And this is definitely less than 2/3. So this gauge invariant operator hits the unitary bound, which means that there's something sick about it. So what happens is that along the RG flow, you acquire anomalous dimensions, and as soon as it hits the value 2/3, this field decouples and becomes free. So this operator just becomes free. So we have to remove it. Or like below that point, you have accidentally one symmetry just acting on this free cutoff field. So there is accident. So need to add that new one to the minimization process. So one quite effective way of implementing this is to now add a Lagrangian multiplier field. And add trace lines to it here. So through the F-term condition, this will project this trace lines square out. And also, it's quite safe because you already know that this is actually relevant. I learned this very recently thanks to Simone. By the way, this presentation is it's a simplified version of my papers. Our paper has more terms, but after some analysis, it turns out that many of these terms will actually not contribute to anything. So this is the simplest version of this n plus 1 p. Okay, now after adding this term and do the motion, this motion again. Then it turns out that now I get rational value for the arbitraries. It goes like this. So now I have to zoom into this, which means that the dimension is 3/2 of R, is 6 feet. So that is the dimension of the A2 or just the Coulomb range operator or just and also by plugging these numbers to the formula of the lagrangian that I just erased, you get n so you get the same number that you expect for Rogers Douglas theory. So my claim is that this gauge theory describes Rogers Douglas theory at this point in the outline. You can do further checks by computing superconformal index. Because now I have a gauge theory description, I can use localization to compute the full superconformal index to the most general form. And you can compare that with the result of the chiral algebra or the prediction from the TQFT formulation. And it agrees. So that gives another check of this algebra. So, any question?
So n becomes Coulomb parameters.
Right.
What about the rest? They all decouple or what?
No. So you can form a gauge invariant operators from these elementary field. And the trace lines clearly decouple due to this extra. But it turns out this singlet operator N. So it started its life as a singlet in high energy, but it ends up being an operator that parameters the Coulomb range. So that's very weird, right? Because if you look at this matter content, giving a value to N, it's not going to break the gauge symmetry. So it looks totally bizarre. So that has been the greatest puzzle for us.
Is it even obvious that it's a flat direction from? Or is that also a non-trivial statement?
Well, it is a flat direction. Yes.
Excitation, I guess phi is equal to 0, so
Is
There's no split potential, right? Is it?
I don't see any superpotential.
Because the phi decouple, sorry. Is it correct? The fact that 5 decouples means that there's no superpotential?
Well, I mean, this is the IR superpotential kind of. But it's trace phi squared that's decoupled, but phi itself is there.
Right.
It's not a gauge here at all.
So you have to impose the that term conditions.
Right.
Just asking. To show if n is a flat direction, do you have to impose the that term condition?
Yeah, I thought that was a definition of it.
Right.
So here I'd like to give you some kind of argument why it may make sense to identify this as a Dornish parameter. So let's see what happens if I give a back to this n from this lagrangian. Then that will change my superpotential. Actually, I think I should do something before that. Let me study this RG flow in more detail. So if I turn on all the superpotential, then the matter content such what I join SPC with say NF equals 1. So usually the number of flavors is twice the number of points. So you typically Q and Q twiddle to cancel the gauge on. So this is like effectively NF equals 1 thing. But this potential breaks that in one global symmetry. It's kind of peculiar to interaction. So if I turn off superpotential, then V, I have adjoint SPC, and it's going to flow. It turns out it flows to some fixed point, for W equals 0. And along this flow, it turns out trace phi squared gets decoupled. So even for turning on that interaction. Now, let me call this optimist lambda 1 and lambda 2. Let's turn on lambda 1 and lambda 2 direction. So lambda 1 direction is a relevant information. So its dimension, its R chart turns out to be less than 2. But the second term, lambda 2, is irrelevant direction. So it attracts to this point. What you find is that there is another fixed point for this time, where this m phi q reverses direction. So the parallel RG flow goes like this. So it turns out that this is the H0 point. It's quite straightforward to do this kind of analysis. The only thing you need to do is A maximize with respect to some symmetries. And also you can, just for fun, A at this point is something like 0.453, and A at this point is 0.366, and A at this point is around about 0.358, so A indeed decreases from the large flow. So what happens if
How is this computed? How this flow is computed?
Oh, it's just computed by A maximization. So if I turn off W equals 0, then this R phi, R cubed, they don't have any relation.
Okay,
But
so
you can still maximize A to find different R charge.
So you have 4 points in this graph.
Yes.
You don't have the roots, the flows, right? You don't have the flows themselves. You only have the endpoints. Only 4 points in this graph. You know.
Well, I can start flowing like this, or if I just keep this coupling to be non-zero, generically it will derive simplified stuff from here.
You think that you just know the A value only for both points?
Oh, A is for just for the fourth one.
Yeah, it's not that you have the whole floor.
But
And
near each point, you have the set of anomalous dimensions of these operators, also from the bar chart for the kernel operators. And so there's a kind of probably a unique with this few operators.
Okay.
Could I'm sorry, to go back to the question of the moduli space, it's just,
Yes.
I can see that there is an M flat direction, but it's just not obvious to me that that's the only flat direction from that superpotential. So if I set n to 0, is there another branch sticking off involving, you know, q prime phi, q prime type operator?
And what's your Q prime generator? Is a direction?
Yeah, it looks, for instance, that, right, for instance, I could turn on q prime, maybe I'm wrong.
I haven't tried.
Okay. I mean, because you got the central charge, right? You want to think that this fixed point really is that n equals 2 theory, but it would be a surprise, though, if you have an extra flat direction staying.
Can one see where the additional supercurrents come from?
That's an interesting question, and I don't know for sure. That's not possible. So, about this moduli, when I give a vector, then, so I will make sort of pictures that go like this. So if this theory, so if I give a vector to n, and if it does flow to IR, then in the IR, this guy and this guy should have same R charge too. So once I give a vector n, that says R of q is equal to R of q prime. And now, okay, I have to erase all the equations. Using this relation and also the anomaly cancellation, it turns out R of phi ends up being 0, and R of q becomes 1. So having R charge for the cube to be 1 means that I can add a mass charge. So this is like giving a mass charge of the cube. So this is now gone. And now R of phi is 0. This is kind of weird looking thing. And one thing that I tried is to compute the superconformal index using this weird charge assignment. And it turns out that if I plug in those values, then all the off-diagonal components cancels out. And you're just left with the free n equals 2 vector. So the formula goes like this. So I have the vector multiplet and the integrants for the adjoint parallel, for q's and q prime. And if I plug in those values, then this thing has Cartan piece and this off-diagonal pieces. For the experts, I think this involves elliptic gamma function that has more of a gamma z plus minus 2 for this type. And there's also 0 more factor that goes like this. And this thing contributes to gamma z plus minus square because R chart is 0. So typically I should have P cubed in R over 2 here. But since R is 0, now these things cancel. So the off-diagonal components goes away. And there's also the part-time piece that I erased here. So, and also that's true for these q's as well. So I'm just left with n equals 2 vector, or 3 vector. So this is a argument why this
So that would imply that there's an unbroken U1.
There's unbroken, right, there's unbroken U, and there's a free photon floating around.
So what happens if you turn on, you go on the Q prime branch?
I haven't checked whether there is a branch.
I think it's obviously the change, isn't it?
No,
I don't think there is.
There's not.
I think the point is to make a gauge invariant.
The phi equation tells you that the atoms that you can form from Q is zero. The form gauge invariant can be both Q prime.
Yeah, the point is you can't make a gauge invariant just out of Q prime itself.
Oh,
It's
right.
anti-symmetric.
It's
Okay.
decided to 0.
I think that's the resolution.
Since the bell is not ringing,
You still have like 3 minutes.
okay, for the remaining 3 minutes,
But you don't have to. Okay.
but I'd like to. For the remaining 3 minutes, I'll give you a description for H1 theory. This is going to be brief. Because you just repeat the same procedure but with different lagrangian. And interestingly, the matter content is still the same for the H1 theory. The diffraction term is different. It goes like this. So this is a much more familiar term in the context of cyber dual. Now you can assign varying charge +1 and -1 to the Q and Q primes. So this theory preserves U1 global symmetry. In addition to this U1R and U1F that can be mixed with R symmetry. So it has U1. So R of IR has to be some linear combination of this R minus F. And that can be determined by A maximization. And you repeat the same procedure. Also, I need to add this term. Because we already learned that to adjust the flow to W equals 0 point, you will decouple trace by square of the flow. That can be submitted by this term. And you run the same machinery, and then you find that A is given by less than 4, C is 1. That is the value for each one by, for example, Shapiro and Chicago.
What happens if you increase the number of flavors?
Number of flavors again?
Put more flavor to prime in that theory. Is that leads to anything interesting?
Okay, there is an interesting thing for 2 flavors. Actually, if you have 2 flavors, it flows H2 theory. If you tune some interaction, it's not exactly this one.
So you can show that by integrating out you flow from that theory. You mask the flavor and then you can check for another consistency check that you can flow from.
Yeah, I think so. I think that can be done. No, I haven't checked myself. No, actually for this guy, for H1 theory, you can integrate out the massive modes and you can actually flow H0. Okay, now I'm not 100% sure. Yes?
Regarding this H0 theory, can you construct additional operators of dimension 3?
Dimension 3?
Yeah. I'm just wondering whether you can construct an operator that might be candidate for this additional SE2.
I think in principle, yes. I haven't tried hard to figure out which is the right combination. So since there's an extra SE2R concern, you should be able to find some combination of this field that generates that current. And if you come to the superconform index, you can actually convince yourself that there is such an operator.
Oh, okay. Any good combination?
From this point of view, don't you have to worry about whether you generate other terms in that superpotential involving the chiral field strength field for the SU2? In other words, W alpha dot square or so forth are there. I just,
Here I just don't see how to write any other terms beside this for a given arch. So if there is some operator, let's say arch try 0, then you could have like some polynomial of that. But
Right.
here I don't. So, and pretty much, I think it's possible to classify all the operators that has arch equals 2 by combining these things. And that pretty much restricts that you can do.
You do see like the photon field combining with the ratios apply, right? You take trace value of the developer to see the
right.
photon field.
I don't know.
So
That's how you see that there's like a U1 photon field in this sense from trace value.
So,
By the way, I think this is the right time to pause. Okay.
go ahead.
Okay, let me start the second part of my talk. So, so I have given you some weird looking n equals 1 gauge view that flows to this n equals 2 CMT. So you might want to ask, how did we get it? And it has an interesting story that like we never thought of getting it, even though we actually wanted. But we were doing totally different project. That is to start study some n equals 1 supercompound field theory, possibly non-lagrangian theories, and build some new set of n equals 1 non-lagrangian field theories from some known n equals 2 supercompound theories. So, and let me describe the procedure. So let's start with n equals 2 theory with a global symmetry. Play with your, let's call it Gn. Then this theory contains a momentum operator field, so which belongs to Lorenz-Morris notation, belongs to this B1 hat. Sorry that I cannot translate this to Kent's notation real time. Maybe you tell me. But so there's a scalar operator that belongs to the conserved current multiplier. So this B1 hat contains conserved current, and this is a bottom component, and that has SU2R charge in the I3 So now, using this, I introduce some chiral multiplier. N equals 1 chiral multiplier, which is in the adjoint of this flavor group G. So this also transforms to the adjoint of the flavor group. So I can try to write this interaction. And obviously this is going to break the C2R symmetry down to C2 times U1 to U1 times U1. And for, I'd like to call it U1 plus and U1 minus, where the generator is U1 by J plus and minus, and this is actually nothing but the arcans of this guy. This notation is actually motivated from this 40 n equals 1 class S construction, which I'm not going to talk about today, but it's what has been convenient for us. from this this notation, operator mu has charge 2, 0, but M should carry charge 0, 2. So here U1 plus and U1 minus are just candidate R charges. So under any candidate R symmetry, superpotential should have R charge 2. So I have these two, this operator mu and this chiral superfield M that has charge 0, 2. And superpotential should always have 2, 2. And the supercomponent R charge, R symmetry has to be given by some linear combination of these J plus and J minus. This is some combination. This is the combination that we have. And epsilon can be fixed by a maximization. Even though this term breaks n equals to Suzy explicitly, actually if you run the RG, and it turns out this is marginally irrelevant operator. So as you scale down to low energy, this term actually drops out. So in order to make it really interesting, there's a black fraction parameters by n, and I give a value to this by n. And specifically, I will be giving the potent vacuum expectation value, where sigma plus is this raising operator of SE2, and rho is embedding of SE2 into the flavor group GF. So, for example, I can choose, so if GF is SUN, choice of rho is in one-to-one correspondence with the partition array. Maybe Jack already told you last week about classifying this.
But who remembers what we did last
So, yeah, I mean, I can give you a simple example of it. I can, you just write down in terms of Jordan model form, like if, say this is a 5 by 5 matrix in SU5, then I can pick the partition that goes like 3 plus 2, and I divide into 3 factors, and give this value. And that's one my choice as well. And this partition, you'll just partition this n by n matrix. So you can do play a similar game with SO, SP, or even exception groups. Exception groups are classified in terms of what's called Bala, Archer, label. It's more complicated, but it can be done. So my goal is to study
So n in your convention, as I mentioned, which is correct. Capital N is the
yeah. Well, in the UV, it's three chiral multiplied.
Okay.
And mu is a momentum, it's a bottom component of the tensor current, you should have mentioned. But now I'm going to give up there. Labeled by rho. And this will trigger our flow, of course. And in general, we expect that we land on N+1 superconductor field theory, where the global symmetry is broken by this choice of rho. So the global symmetry is given by the commutant of rho. Sigma plus. And I will call this n equals 2 here as TUV, and let me call this as TIR. And T of IR is specified by first choosing the derivative UV. This is n equals 2 C of T, and the choice of the SU2 vector. And this is going to give you some n equals 1 C of T, which has n equals to origin. And the global symmetries for the case of SUN, it's easy to identify. Like if you have a Young diagram of this sort. N1 so on. And the unbroken global symmetry is something like this. Or the people who work on classes, this is your bread and butter.
The ends are the ends of the partition?
Yes.
Or, okay.
So now this, yes?
Sorry, did you say that your web is important? So then, shouldn't you just look at the commutant of just the one part, and maybe that's what you're doing? Yeah. Okay. Sorry.
So one nice thing about this nilpotent deformation is that actually you don't really need to know Lagrangian to study this kind of deformation. It was kind of surprising for me that it's relatively harder to study usual mass deformation, non-nilpotent ones. But
I guess actually, the question was, so that symmetry algebra is the centralizer of the SL2 embedding corresponding to that choice of nilpotent. I mean, in general, the centralizer of just the nilpotent guy is bigger. Right? I mean, so if you tell me what the nilpotent is, then that determines, a whole embedding of the SL2, right, the algebra. And the centralizer of that is what you wrote over there. So is that, I mean, what is the symmetry algebra? Is it just the centralizer of the nilpotent, or is it the centralizer of the corresponding SL2 embedding?
yes, you're right.
Which is it? That was a question.
Which one?
Yeah, is it that or is it that? They're different in general.
Oh, okay. So I meant to this.
Okay, so it's the centralizer of the full SC2.
Yeah.
As it were.
Oh, okay.
But your web does not know about the full SL2.
Well, I mean,
or do
we
you
construct it.
No. The thing that he's actually using in his web is only the.
Well, I suppose not, because he only writes down W, but the Lagrangian presumably has the permission conjugate, which presumably involves rho sigma minus. So, in some sense, it already sees the whole thing. I would guess.
So,
How much is the difference between those two values, between the two rules?
Well, I know one's in general bigger than the other. I don't know offhand what.
What the things raw sigma.
Right.
now the upshot is that, like, once you know the essential charges of the TUV, I know A, and C, or the Flavor essential charge of this type. If I know these, and then I can use A of ion, C of ion, and K of, let me call these numbers plus just by the choice of them. So it's almost entirely determined by group theory. So let me just give you an outline how it can be done. By the way, this is due to this nice paper by Ade, Yoshi, Tachikawa, and Hamilton. They studied these kind of information. One useful thing to do is to first decompose adjoint under this invariant row in the following form, where Bj, B sub j, is the spin j, irreducible representation of SCT. And these are like a representation of the centralized H. And for example, I can give you one choice. Say adjoint of SU3. If I pick row to be partition that looks like this, 2 plus 1, and you remember that adjoint is really same thing as 3 times with 1 minus 1. So what I'm doing by this choice is that I decompose fundamentally to 2 plus 1. That's what you do in terms of matrix. Then if I plug in this back here, then adjoint is 2 plus 1 times 2 plus 1 minus 1. And here you get 3 plus 1 plus 2 plus 3. So in terms of this notation, it's a spin 0 and twice the spin half plus spin 1. So I can decompose adjoint of C3 in this way. So this is just a decomposition of matrix in some particular basis. Nothing super fancy. You can be more refined and keep track of the charges for H. But for my purpose, this is not. So it's nice to decompose in this way because then I can easily map this row sigma plus in that kind of basis. So now I'm writing each element of this the matrix in terms of that basis. So this is what can be written the following, and one. So J's are the labeling of the spins, and J3 are its the weights in the representation. So you can decompose it this way. And so you can immediately see from this term that if I assign, so I originally started with assigning J plus J minus for U to be 0. Plus J minus was 2, 0 for U and 0, 2 for M. But as I told you, this thing should have R charge too. So which means that R charge for
so the coefficient in front of mu is set to 1 because
Yeah,
that's your vector,
yes.
you're saying. And you're not, you're fixing the vev and allowing deviations of m along the direction of the vev, or is, in other words, why isn't that 1 plus m as the coefficient of that the mu 1 minus 1.
Here?
Yeah.
I'm just setting it to 1. Yeah, and it should be something like that.
But you want to keep track of the
No,
of the
I'm
field.
assuming that this close to the CFT. So at the CFT point, this operator should carry out. So that's an assumption. Actually, it turns out not every information flows to CFT, but almost all of them does. So yeah, in order to preserve R symmetry, I have to shift the J plus minus charges in some way.
Basically asking
Can we see that
the fluctuation.
this kind of shift will do the job? It will preserve 2, 2, right? Because this guy has row symmetry minus 1, so it will make the J plus and J minus charges to be 2, 2. So to make it short, the effect of deformation can be simply characterized by shifting these J plus and J minus charges. And you see that you actually need to know this time. And in computing with A and C anomalies, they are written in terms of trace R cubed and trace R. And R is a linear combination of J plus and J minus, which means that if you know like J plus square, J minus, J plus cube, and these kind of things, then you can actually deduce these central charges in the IR. Thanks to just this shift. But there's one extra piece that I have to consider, that is we added in this extra field ends. So we have to take care of these. But one important thing is that not all the components M will remain coupled. Some of them will be decoupled. So we only need to keep track of the components of M that remains coupled in the end. So after some long sum events, actually it's not at all. Let me give you an argument. So once you give a vec to M, then that will break your conserved current in the UV. So some of the components of the conserved current will be non-zero. And you know how much has been broken through this potential. So this is a term that breaks the flavor symmetry. So the component of that is simply determined by that, which in this case is given by this. And that's generally non-zero. So after giving a vec to M, that will break the conserved current in that vacuum. So and that is characterized by that. So anything that appears on the right-hand side of this conserved current, so this should be non-DPS. So this should combine into the conserved current multiplier to form a normal. This is non-DPS. And these non-DPS operators can never enter into this proportional coupling because they will end up being relevant. So if you look at this term, anything that couples with this, it should be dropped out. And there's only one component that can never appear on the right-hand side, which is J comma J. So mu J comma J, it never appears on the right-hand side of this thing. So this guy still remains to be DPS, and that is conserved. So in the end, what you find is that this potential just truncates to this form. Because this is the only DPS operator on the components of mu. So that allows us to label these singlet fields after this. And this the number of J's is just determined by its group theory. So here I have 1 and 0 and 2 and half and 1 and 1. So through this decomposition. So this is is all we need to know to compute this conformal anomaly. So we first start with A of E, the trial R charge, and then compute the shifted one, and add in the contributions from the singlet field. And that will do the job. And then you can compute the central charges on the other end. So it's quite straightforward. You can put it into a computer if you wish. And up to the caveat, which is that some of the operator might hit the unitary now, then it gets decoupled. It can get decoupled. This is something that we've seen just a moment ago. So we have to take care of that. And I don't have a reverse argument, but for many cases, it seems that the operators that can be possibly decoupled are the full branch operators. Full branch operators in WB in this or the single field N that components of N. So for all the practical purpose that I did, we checked the dimensions of these operators that we know, and also the dimension of these operators. And if it hits it goes below the unitary bound, I remove them. And if everything stays above the unitary bound, then I keep it. So this is all mechanical and put it into the computer. So that's the thing that we have done, hoping to get some interesting class of n equals 1 CFTs. But, as I told you, we are instead getting some nice n equals 2 CFTs instead. So for many interesting cases, we ended up finding n equals 2 CFTs instead of n equals 1. So here's one example. So let me start with the theory. This is the fourth theory, which is the same as SU2 with fourth layer. This is n equals 2 SQCE. And I have a choice of this embedding. This is labeled by a partition of A, some D4 type partitions, which means that the even number should appear only even times. So there's, for example, there can't be no A. So this is one, these are full classifications of SU2 embedding for SOA. And for this guy, the remaining global symmetry is nothing. For this guy, I also get nothing. For this guy, I have SO3. This 5 plus 1, 1, 1.
Do you see some signs of triality?
Triality? I don't see triality here.
You did get the same models, but 4-4 has 2 orders.
Okay, yes. I wanted to skip it, but it turns out that.
Yeah, but so the triality is about 4-4 and what is it?
5-1 cube.
5-1 cube.
The thing
All
about
of
it,
them go to H1.
right about 5-1 cubed.
5-1 cube, other than that one. Right, so those three models should all go to the same thing.
Yes, you're right. You get the same theory.
And
Right.
you seem to have consistency with reality with
Right.
the other method, which is 2
2 to the 4 and 3 1 to the 5.
Yeah. So this is a pattern that we have seen. So for the first 5 lines, we get something interesting. For this choice, I get H0. And this is how we were able to write down this Lagrangian for this gauge theory, SU2 or 1 flavors, blah, blah, blah. So and you see that these singlets are nothing but the reference of these guys. And you do the same thing for this partition, then I get H1, but there are actually 2 choices to get H1s. And actually they
Three. And they're related by triality, that was what Alvin just said.
Yeah. But actually I couldn't find any difference between 1 and 2
because
in this information actually.
yeah, I see. So you're deforming by an adjoint, right? It's a nilpotent element of an adjoint, and I suppose it will not see the difference.
Okay.
It's a difference between two streamers.
Yeah,
But
but
you
these
don't have
two
any-
ones actually give you a different action. So in some sense, it realizes some kind of cyber-like duality. So because
The
you
second
get two different
charges are
lagrangians.
big. They flow to H1.
Right.
They flow
So
the
they-
same H1 theory, but their UV distribution, well, intermediate
I mean, I'm not-
distribution is not the same.
I mean, the two Hilbert orbits in the adjoint are different, and they are related by, reflection, exchange of the two nodes of P4, right? I mean, so, I mean, okay, I'm not sure what to say.
Yeah, well, I'd like to know if there's any subtle difference between 1 and 2 that I've been overlooking.
No, but it's the difference between 1 and 2 and the difference between those and 5-1 cubed, just trial. I mean, so if you can tell the difference between 5-1 cubed and 4 squared, you can tell the difference between the two 4 squares.
You could also ask if you really see the difference between the neutral orbit of O of H versus neutral orbit of S of H. And orbits of O of H.
Well, in this case, the real true global symmetry is SOA, not OA. So,
Okay, then you should definitely see the difference between one
all right, yeah. Please tell me after. So, and this choice really realized H2. So I got all the H0, 1, 2. And for all of these choices, I just get Jaewon N equals 1 CFT.
And how do you
The reason why is that I'm getting irrational center charges. So you can argue that if you get an irrational center charges, then it cannot be N equals 2. I'm not sure there is a rigorous proof of that.
Do you see anything special for the case of 3, 2 squared 1?
3, 2 squared 1. No. So for these guys, I haven't seen anything special. For these guys, especially this one, has some weird looking center charge. 6,349 over 100, 13,872, something like that.
And is there a reason why you don't see the full flavor symmetry of H2?
Oh yeah, here I don't see flavor symmetry from this choice of vector. Somehow the flavor symmetry gets nets in the IR, and I cannot see that from this higher. Yeah, it would be nice.
So they're missing the currents that.
So yes, so the conserve there is extra conserve current that whether it is 3, but it's not obvious from the lagrangian that you're writing.
So is 5-3 is N equal 2 or N equal?
This, it seems this is N equals 1. I don't. find
Doesn't it violate the N equals 2 bound on C? So wouldn't that tell you that it's N equals 1?
Let's see.
Isn't C basically 1/3? I mean, 11/30. That looks like 1/4. Maybe I'm just doing my math wrong.
What's the bound?
The 311, right?
Yeah, so there's this half for the N equals
Philip was talking about C.
No, I'm talking about the
C.
C has, for N equals 2 conformal field theories, has to be greater than 11/30.
Oh,
What is 11/30 compared to 35, 138?
very good. Good point.
Oh, is it?
I haven't checked, so you can check
So much time.
I think.
Does it violate?
One is
Yeah, so if you look at our paper, we have a large list of, large table of these rational numbers.
Yeah, it's about.
So it's kind of interesting to see rational numbers on the rational set.
It's about,
It's a quarter, so it's less.
It's
smaller. So
Yeah, so
there's an argument that that's not an N equals 2.
Okay, great. Awesome. All right.
So
That's-
just out of curiosity, is triality preserved for the 2 to the 4th and the 3, 1 to the 5th? That those actually flow to the same theory?
Oh yeah, I think it does. Let me check.
one, it's...
Those are different theories. N equals one theory, so they're yeah, whatever that is, you can identify.
So these are clean.
No, those guys, yeah, those guys. Those
Yeah.
or three.
I don't have it in my picture.
SO5.
Yeah, SP2 is SO5.
But the question is,
yeah.
did you get the central charge?
It's a good start.
We wouldn't know the central.
So are you selected by child?
But that's just computed from the...
But you should get the same A and C.
Okay,
For those guys.
I can tell you
I
after my
mean,
talk.
it's there. You see 2 to the 4th, that gives you SP2, and 1 to the 5 gives you SO5, so it's no surprise there. The HF is...
No, but having the same global symmetry is never enough, right? Here, we still have the same global symmetry, but we
With different theories, that's right. No, you want to see.
Right, no, you want to see the central charge.
Yeah.
Central part.
Okay, so
Okay.
that's one piece of data. I can entertain you more by... So one set of theories that we studied is this rank 1 CFTs that Philip and friends have discovered. As long as I have A and C and K, then I can run this machinery to compute the central charge in the IR. And it turns out among the rank 1 CFTs, only these guys, not just 2, 4, 5, 6, 7, 8. So for these guys, if I choose rho to be what's called rho principal, that is the choice which breaks the global symmetry maximally. Or there are some other choices, sporadic ones. And for this choice, it always flows to H0 theory. And if I choose other things, then it can actually flow to H1 or H2. In all the other rank 1 CFTs, we couldn't find any SUSY nets. Also, and we can do more, so other. Other interesting cases, say I can study this TN theories in classes. They also don't exhibit SUSY netsman. There are cases, these are basically summary. SUN with that is 2 and 3. So this guy has global symmetry U1 times SU2n. And I'm not touching this, I'm only breaking this guy through important fair. And if I choose my partition to be just n, the principal embedding, then this guy goes to
N or 2N?
2n.
Okay.
A1 and A2n minus 1 theory are just relatively. And I choose this partition, 2n minus 1 plus 1, which will preserve U1. And it turns out it flows to A1 comma E2n. So this E2n theory generally has SU2 times U1 global symmetry. So the SU2 is not really visible from this description, but it kind of emerges in the IR. I can also do similar thing for SN with 4n plus 4 flavors, which will give you SO4n plus 4 global symmetry.
It should be 2n plus 2. Oh, this is a N equals 1 theory.
No, this is the theory. SP1 should have SO8 global symmetry. So it is.
So you should set the number of levels to be 2n plus 2.
What?
The convention is that number of levels is 2n plus 2.
Oh, yeah. So,
2 and
Counting
2 and
half.
he's counting half hypothesis.
half.
So multiple.
Half NF is Half an F is
2n is. Then for the principal embedding, I get A1, A2n. For the row 4n plus 3, 1. For the row 4n plus 1 or 1 cubed. This will preserve SO3 symmetry. That gives you A, E, R. So these are the full list of adjustable spheres we were able to construct.
So,
Yes?
there are of course lots of other partitions.
Yes, there are lots of
And they flow to n=1 theories that we don't.
So, yeah, it turns out if I choose all the other partitions, so we went through research, these are the only examples where I can pinpoint n=2 fixed point.
Okay.
For general choices of partition, I get irrational central charges, or sporadically I get some rational central charges.
And do you always flow to non-trivial n=1 fixed points, or do you have sometimes just flow to?
That might be the case. I haven't really checked. So that, yeah. I definitely need further investigation. So far we only tabulated the value of central charges.
Mm-hmm.
In principle, you can also try to compare indices or lots of other things. But there seems to be some sporadic examples where I get rational central charges like this. And we couldn't find a noticeable pattern. But there's some pattern that we were able to notice. Yes?
Is address still classified?
I mean,
The answer is
how would
no.
you define address?
So there could be sporadic.
I mean, there are some large class of constructions. Say you can build it from type 2B on Flavial singularities, or M5 rings on sphere with some punctures. So you can classify those particular classes of theories. And many of these theories have this rational scaling dimension of long-range operators. So if you define that as a defining feature of F-Barges-Lowers theories, there's some nice set of examples.
Yeah, I mean, you always run into trouble that there are an infinite number of theories with rational scaling dimensions for the long-range operators. So in that sense, you don't win. I mean, I think you declare this set of theories are our Jaewon-Douglas theories, and therefore are classified them. Right. Yeah.
Okay, so there are other examples where AD theories flow to another type of AD theories. So the key observation that we were able to make is that it seems n=2 CC enhancement happens only if let's say the UV theory that I started with will have central charge C. And I can associate the Carroll algebra to this guy, and CO2D is minus 12 CO4D. And if CO2D is also KO2D, if C and K satisfy Sugawara relations,
So the first one, what?
Sugawara relation, so CO2D is given by CO Sugawara.
Oh, so, okay.
It seems this is a necessary condition to get any n=2 S. So, and I don't think this is
Was the minimal levels or mostly was minimal.
sorry.
When you say Sugawara, what do you include?
Well, I'm saying that this theory, UV theory, will have the local symmetries back. So if the Carroll algebra is simply given by a finite symmetry algebra of this type,
So
on a certain level,
what's the meaning of this?
then it seems there's a chance of getting Suzy answer. I have no explanation why that has to be the case. And also, actually, there's a case that, so this is only necessary, seems to be a necessary condition, not sufficient. But there are certain cases where this is satisfied, but it doesn't have to do anything at all. So it seems this is a necessary condition, but I don't know where it's coming from. Also, another thing is that, this case, is that Suzy enhancement happens only for this choice. So when I choose SU to embed into a principle, then it enhances to n equals 2 in the IR. But if this doesn't happen, then it never, all the other choices will never enhance to n equals 2.
So this is for classical algebras, global symmetries.
I also checked the exception groups, E6, 7, 8.
What were the starting theories?
That's the one satisfied this condition. So for the Minan-Lensky, say E6, that has level -3. And all the machinery that I gave you doesn't really rely on lagrangian, so I can just run the machine and compute A and C. And this time, if I choose flow to principle, it flows to H0 theory. But there are other choices which enables us to flow to other A theories.
You could do it for EA?
Yeah, it also works for EA, like you said. But the thing is that if I assume there is an n equals to CFT with G2 and F4, with this central charge that is fixed by assuming it realizes in some arbitrary space, and it doesn't enhance to n equals 2.
It does not.
It does not.
Does not.
Does not. So of course, actually one of these theories are ruled out by the recent paper by Tachikawa and friends.
But you could take other nilpotent topics. You don't have to take
Other ones.
You don't have to take the minimal of it.
Yeah. I mean, so my observation is that
Start with the minimal of it. You start with the minimal of it. You perturb by the principle. Right? You don't have to start with the minimal. You start with some other model spaces.
What do I say this meaning?
Take the next minimal of it of F4 and G2.
Yeah.
And for F4, minimal of F4 and G2.
Sure, and that's how you get these other guys from E6. So if you choose the minimum one, or like the principal one, then you get H0. But if you get next to the minimum one,
There are
then
two
you
things.
get
There
the
are
other
two
things.
things. You have the starting theory, and you have the particular orbit you perturb. Okay? Now, you pick as your starting theory the minimal orbit. You could pick a different orbit,
Yes.
a different theory. And I don't see that you did it. What do you say?
So you're saying, what if you started at the rank 2 E6?
Rank 2 E6. Yeah, the rank 2 E6 doesn't satisfy this relation. And as far as I checked, it doesn't intersect to for all the choices of orbits.
Yes, and if you say that minimal F4 doesn't work, then you could start with a theory which is slightly bigger. Which is
But that's against the objectives.
Yeah. My point is that if there's no enhancement for this, then this is experiment. That all the other choices will not exhibit enhancement. That's just.
But I thought you argued that rank 1 theory is in F4 as the next to minimal in F4. Not minimal.
So it doesn't satisfy the super, but there is a, right, there is
Well,
a,
not clear. You didn't try.
Let me finish with the second observation. That is, the second thing is that if rho, or let's say next to minimum, it shows n equals 2 enhancement only if it saturates this bound on the flavor central charge.
that's not what I said, but I take it as a comment.
This is independent, so I'm just saying that same observation. The observation is that this is to be necessary for this choice of orbit to exhibit SUSY enhancement. But if you want to have further SUSY enhancement for other choices of the nilpotent orbits, then it seems this has to be this equal has to be saturated. So that's our observation. We don't have either proof or counterexample of this fact. This is all experimental. So, yeah, I kind of hope to say there's some interesting connection to the chiral algebra, but I cannot make it precise. Let me just list some obvious things that I'd like to know. The answer that is generalize this construction to other larger cellulose type theories. There are like many generalized versions of AD theories. Or is it always, more ambitious question that is it always possible to find some gauge theory description of these non-Lagrangian theories? I don't think that's true, but maybe. Maybe some classes can be constructed. Since you know some gauge theory description of AD theory, you can try. One thing that would be nice is to derive the cyberlimiting geometry in some way using this gauge theory description. So that would be really great. And regarding the SUSY enhancement, there seems to be a pattern, but we should understand why and how. So it would be interesting to know why it happened. And also, this particular type of deformation, we are motivated from the class S construction. So this really means that for n equals 1 class S theories, there is this flipping of coloring of punctures. So that you are like flipping this moment map and to this sequence. So like a dual meson. So these constructions, some of these constructions do have a class S picture actually. So you can realize just the class S if you allow to use some irregular punctures. But the thing is that if you fix it, then the class S picture tells me that it should flow to n equals 1, but it's actually flow to n equals 2. So there might be some string theory reason why this is happening. That would be really interesting to figure out. Okay, let me stop here. Thank you very much. Yes?
So once you fix your UV theory, what kind of computation gives you A and C for your, what I'm asking is, how does it depend on your choice?
Oh,
is it easy to...
Yeah, that's first encoded here.
Okay.
So if you choose row, that will shift the amount of this one of the candidate R charge in R charges. And also at the same time, this choice will tell you what kind of the singlets will remain coupled. So I already erased it, but in the end, you get this type of function. And this amount of m sub j, is just purely determined through theory.
So how do you get something that's non-rational? You said there's some choices for...
Oh, you have to do A maximization. So this is not like fully determined by Lagrangian. You have to run the A maximization, and then generally you expect to get irrational central charges.
So in your exploration of the rank 1 cases, did you also look at the ones which are the discretely gauged versions of them? Those are give realizations of the ones with G2 and F4. They're not they don't have them. They don't saturate those bounds. They're just different rank 1s. Did you look at those as well, or?
For G2, I'm not sure. I think when we write a paper, we just search through one particular table of your papers.
Okay,
I'm not sure.
so maybe, because it could be those ones which are very closely related to, for instance, the E6, 7, 8 series.
Oh, through discrete.
They're just through a discrete gauging. I'd kind of strongly expect that if those guys flowed, the discretely gauged ones would as well too.
So that's the
Level, right, that you were talking about. Okay, there are no further questions. Thank you.